Hello students, welcome to Educate. Today we are going to study the concept of torque and angular momentum. So torque is given by force into perpendicular distance F into D. Torque is a vector quantity and its direction will be perpendicular to the both of force and displacement. Generally, it is written like in case of vector, we write it like torque equal to R cross F. Let's do one evaluation. Suppose vector R is given as 2i cap plus j cap plus k cap, and vector F is given as I plus 2j plus 3k, and it is in Newton, and this is say in meter. In that case, what would be the magnitude of torque? So to find magnitude of torque, first of all, we have to evaluate R cross F. So for this, we write I, J, K, and then coefficients of R2, 1, 1, 1, 2, 3. Then we evaluate. So R cross F, which is torque, is equal to. Here you will take I cap common, then this will be left. So 1 3 is 3 minus 2, so 1, then minus j, and then you will leave this column, this row, 2 3 is 6, 6 minus 1 5, and then k, and then you will leave this column, this row, so 4 minus 1 3. So you have got I cap minus 5j cap plus 3k cap. So this is torque. Now we need modulus. So modulus of torque, which is just torque, equal to square root of 1 square plus 5 square plus 3 square. 5 square plus 3 square Newton meter. So you have understood how to find torque if R and F are given. Then comes angular momentum. So angular momentum L is related to linear momentum by formula L equal to R cross P, where P is linear momentum. Here same thing we can do, like suppose we want to find out vector L. So for that, if R and P are given, then we find cross product and then we can evaluate. And direction of vector L will be perpendicular to both vector R and vector P. And here dl upon dt will give d upon dt of, this is R cross L is R cross P. Now here we apply product rule of differentiation that says d upon dx of a function a and b gives a into d upon dx of b plus b into d upon dx of a. So here if we apply that rule, so we will get dl upon dt equals R cross dp upon dt plus dr upon dt cross p. Now what we can do, we just evaluate it. So dl upon dt will be equal to R cross dp upon dt plus dr upon dt is v cross p, and if you observe it carefully, v cross p means V cross M into V cross, and these two are parallel vectors. So cross product of the two will become 0. So this term will become 0. So we will be left with dl upon dt equal to r cross dp upon dt is force, r cross f, and if you remember, r cross f is torque. Now, one important result we can derive from here: if torque is absent, if tau equal to 0, then what will happen? Then dl upon dt will become 0, which means L is a constant. In absence of any external torque, angular momentum of the system will remain constant. Here there is one question. Question is, find the torque of force 7I plus 3J minus 5K about the origin. The force acts on a particle whose position vector is I cap minus J cap plus K cap is given. So it is obvious, as I explained to you, that R is given as I minus J plus K, F is given as 7I plus 3J minus 5K. So we have to use the determinant method to evaluate torque. So torque is, first we write I, J, K, and after that coefficient of this 1, minus 1 and 1, and then coefficient of this 7, 3 and minus 5, and then we write I, and then we leave this row and column. So 5 1 5 minus 3. Then we write minus sign here for J, and then we leave this column, this row. So 1 into 5 is minus 5 and 1 into 7 is minus 7. So that is 10. Then we take K and then we leave this column, this row. So 3 plus 7. So we get tau equal to this much. If we want to find out magnitude, in that case we can take square root of 2 square plus 12 square plus 10 square, and we will get its value. Now there is another question. Next question says, you are given, show that the angular momentum about any point of a single particle moving with a constant velocity remains constant throughout the motion. So here we have to prove that angular momentum remains constant. So how to prove it? For this purpose, we will consider force and perpendicular distance, and we will see whether they are changing or not. So here situation is shown. Here particle is moving with constant velocity in this direction. So this is perpendicular distance of line of force. So what we, this is r sine theta, this is position vector r, this is theta. So the angular momentum is L equal to r cross mb, as we have studied. L is r cross p, or L equal to r cross mv. So in terms of, we can write it like mrv sine theta or mbr sine theta, and here this is r sine theta, which will not change even if particle is here. In that case, suppose this is r1, but r sine theta will remain same. If you take another point here, so position is changing here. In this case, suppose this is r2, but still this distance will remain same. Theta will change. So here it will, in this case, suppose this is theta 1. So this will become, its name will change. It will become r1 sine theta 1. But it will represent same thing, OM. In second case, it will be r2 sine theta 2. Right. So here it's given the angular momentum L is r cross mb. Its magnitude is mbr sine theta, where theta is the angle between r and b, as shown here like this. This is direction of b, this is direction of r. So OM is r sin theta is constant in every case, whether you are taking this or any other point if you consider. So here this OM will remain constant, though its name will change. Suppose we are taking this R3 vector, then it will be R3 sin theta 3. But it will represent the same thing. So here R sin theta is constant. Further, the direction of L is perpendicular to that of R and B, that you know very well. So here, and it is also into the page of the figure. This direction does not change with the time. Even direction will also not change. So thus L remains the same in magnitude and direction and is therefore conserved. Now here there is no external torque on it, because if you remember, dl upon dt is torque, right? And in absence of torque, only L be constant. When we say tau equal to 0, then we say L is constant. So in this case, since angular momentum is constant, it means torque is not active. Now, equilibrium of rigid body. Equilibrium means it is in translational equilibrium, it is in rotational equilibrium. It means the forces that are acting to rotate the body, they are equal and opposite, hence net effect is 0. Similarly, the forces that are acting to take it forward, they have also sum as 0. So here the same thing is given, that translational equilibrium is there, and there is rotational equilibrium. It means there is no torque. For translational equilibrium, there is no force. So here something is written that you can read the conditions of equilibrium of a rigid body may be compared with those of a particle, for which we consider earlier. Since consideration of rotational motion does not apply to particle, only the conditions for translational equilibrium. So there are certain cases when object is moving like this in straight line, then translational equilibrium we consider. If body is rotating, in that case we consider rotational equilibrium. So there may be different situation. Here a body may be in partial equilibrium, it may be in translational equilibrium and not in rotational equilibrium, or it may be in rotational equilibrium and not in translational equilibrium, or it may have both things. So we will see different situations. Here what is happening, suppose this is a fixed point and this is a rod which can rotate here like this, and here there is one force and here there is another force. So is it in translational equilibrium? Since point is fixed, so there is no motion. So there is no question of considering translational equilibrium. As far as rotational equilibrium is concerned, so both forces are equal and opposite, so it will not rotate. So it is. In this case, what is happening? Here again, point is fixed, so body cannot move. So translational equilibrium will be there, or there is no question of considering that. But as far as rotational equilibrium is, so here body will rotate, right? So we can say in that case, here the same thing here, the total force on the body is 0. So the body is in translational equilibrium, it will not move, but it is not in rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation. So here rotation will start. A pair of forces of equal magnitude but acting in opposite directions with different lines of action is known as couple. So here one force is acting here, another force is acting here. So here torque will be there. So torque can produce rotational motion. See, the basic types of forces, force will produce translational motion and torque will produce rotational motion. So we can say that torque is a force, or torque is a rotating force. Now let's see, here again same thing is shown. Here Earth's magnetic field exerts equal and opposite forces on the poles of compass needle. These two forces form a couple, equal and opposite forces acting in opposite direction. Here there is another question. show that moment of couple does not depend on the point about which you take the moments. So here, in order to take moments, what we have to take into consideration, we have to take into consideration the distance and the forces. So consider a couple as shown in the figure acting on a rigid body. Here one force is in this direction, another force is in this direction. This force is taken as negative, this is taken as positive, and what is perpendicular distance between them, so that we need, or just we proceed like this. So we take the total moment of the couple will be sum of the moments of the two forces making the couple. So here this is making couple and this is also making couple. So you have to take cross product or take perpendicular distance between force and the point of action. So it will go like this. Somewhere here you will extend it and then you will draw perpendicular. So you will find somewhere here. Similarly, for this direction of force will be just the perpendicular direction from point of action is needed. So in order to avoid that theta concept, we can write it directly as cross product. So R1 times here R1 cross minus F plus R2 cross minus F. This is taken as positive, this is taken as negative. So here, what is total moment of couple? So that will be equal to F, equal and opposite. So F can be taken out, then R2 minus R1. But R1 plus AB, R1 plus AB, see, this vector is in this direction, this vector is in this direction, and this is closing direction. So obviously sum of these two must be equal to this. So R1 plus AB will form R2. So here our concern is to get R2, the distance between two forces here. So R2 will be equal to, sorry, AB will be equal to R1. So R2 minus R1. So that thing is used here. So moment of couple therefore is AB cross F. So we have taken this distance. Here our concern was this point is insignificant. We can take this point here also. And if we evaluate, same answer we will get. In our calculation, ultimately we will get AB cross F. If we change the point to here, that does not matter. Again, we will get AB. So here question says, show that moment of couple does not depend on the point about which you take the moment. Here you are taking the moment about this point, or if you take moment about this point, or if you take moment about this point, you will get same result, because ultimate result will be in terms of force and this distance. So that is why question says that moment of couple does not depend on the point about which you take the moments. So it is clear. Now principle of moments. So here basic concern is when we study about principle of moment. So we say, suppose here this is midpoint, here there is 10 Newton force, and suppose this is 5 meter and this is say 4 meter. This is, if this is midpoint, take this 5 meter and this is 10 Newton. Now what will happen? This will try to rotate the rod AB in this direction, and this will try to rotate the rod AB in this direction, but rod will not rotate. Here it is in equilibrium. So equilibrium condition is again to be considered, but suppose point is not midpoint. In that case, what will happen? So how will you balance? Suppose this is 10 Newton, this is 2 meter, this is say 4 meter, and this is say X Newton. So to balance this, what will you do? So force into perpendicular distance on both the sides, or moment from this point on both the sides should be equal. So 2 into 10 must be equal to 4 into X. Then you can evaluate X. 2 into 10 divided by 4. So it will be 5. So like this. So moment of force will give mechanical advantage also. So mechanical advantage is given by a ratio of forces. So suppose we write F1 upon F2. In that case, distance will be just opposite. Distance for F1 will be here and distance for F2 will be here. So this is formula for mechanical advantage. Now, this is also principle of lever. We will study it later on. While doing some numericals, we will make use of it. Center of gravity. Center of gravity means it is a point. Suppose you are given a body and it is a point where we assume that entire force due to gravity is acting. So sometimes if body is regular, then center of mass and the center of gravity coincide. Here some examples are given, like in this case, body is given. So this is balancing point. Balancing a cardboard on the tip of a pencil, the point of support G is the center of gravity. So here center of gravity will lie. And in this case, determining the center of gravity of a body of irregular shape, the center of gravity G lies on the vertical AA1. This one line, similarly this one, AA1 through the point of suspension of the body. So like this. Now we have one question here. Let's read it and then we will try to analyze it. What is happening? A metal bar 70 centimeter long and 4 kg in mass supported on two knife edges. This is one knife edge, another knife edge is here. 10 centimeter from each end. This is 10 centimeter, this is 10 centimeter, and this is 1 meter. A metal bar 70 centimeter long and 4 kg in mass supported on two knife edges 10 cm from each edge. So 10, 10, 20. What is left? 50. Now, a 6 kg load is suspended at 30 centimeter from one end. Here, this is here, one weight is suspended at this point. This is center of gravity. Earlier, this was midpoint. Now, find the reactions at the knife edges. Assume the bar to be of uniform cross section and homogeneous. So here you have to find out what is a reaction. So we will take moments, and since the rod is not moving, so clockwise and anti-clockwise movements will be taken and they will be equal and opposite. So here figure shows the rod AB, the positions of the knife edges K1 and K2. The center of gravity of the rod is at G and the suspended load at P. Note the weight of the rod W acts at its center of gravity. You know very well. So here weight will act. So weight will not have any rotating effect, but this will have. So in order to counteract, there will be some torque here, so that we are going to calculate. The rod is uniform in cross section and homogeneous, hence G is at the center of the rod. So total was 70. So AG will be from here to here. This is 35 centimeter. And AP here and AP is 30 centimeter, because in our question it is given that a 6 kg load is suspended at 30 centimeter from one end. So total it was 35, this is 10, then this is 25, this portion will be left as 25. So now, so K2G, this portion K2G will be equal to 25 centimeter. This is 25, this is 10, here this is 10, and this remaining is 25. So, but here this is 30. So up to here this is 35, and from here this is 30. So this distance will be PG will be 5 centimeter. So here PG 5 centimeter, AK1 and AK2 are 10 centimeter. That also, as I told you here, AK1, AK2 are 10 centimeter. And then weight of the rod is 4 kg, that will act downward. And W1 is suspended load, that is also given 6 kg. R1, R2 are the normal reactions, normal reactions will act. So up to here there is no problem. Now for the rotational equilibrium, means bodies should not rotate. So force in this direction, force in this direction must be equal and opposite. So we can say here normal reaction R1 and R2 must counteract with the weights. So here the same thing is written, R1 plus R2 minus W1 minus W must be 0. So there won't be any rotation. So we can also write it R1 plus R2 equal to minus W1 minus W. So sorry, it will become, we can write R1 plus R2 equal to 2 weights, forces upward. Normal reactions are upward and these weights are downwards, W and W dash, W dash W. So they must be equal, R1 R2 must be equal to W dash plus W. Up to here, it's clear. Note, W1 and W2 are vertically down and R1, that I have told you. Further, for considering rotational equilibrium, we take moments of the force. So moment of force, that force into perpendicular distance. A convenient point to take moments about is G. So from with this center, we take moment of force for this, and for this it will be 0. So the moments of R2 and W1 are anti-clockwise. Here moment of W1, this is like this because clock, here moment is like this, and we take it positive here. So the moments of R2 and W1 are anti-clockwise, whereas the moments of R1 is clockwise. Its moment will be, moment of this is clockwise. Here this is anti-clockwise. So we can write for rotational equilibrium, total moment must be 0. So minus R1, we take minus R1 times its distance from center will be K1G plus W1 PG. This is taken as positive. So W1 and its distance from center, it will be PG plus this is also taken as positive. So for this perpendicular, this distance should be taken into consideration. So R2 times K2G equal to 0. Now we are given the values. We can put the values in the relations here and here in this equation. And if we put the value in this equation, what do we get? So R1 plus R2, W1 is given 4 and W is given as 6, so equal to 0. So after solving, we will get R1 plus R2 equal to 10G, where G is 9.8. So after that, we will get 98. Sorry, there is some problem. Just wait, there is some problem. Sorry, there was some problem. Now it's okay. So we were discussing about clockwise and anti-clockwise moments of force, and we have taken anti-clockwise moment as positive and clockwise as negative, and we have arrived the situation where moments are equal and opposite, and we consider the rotational equilibrium. So let's continue with that concept, but just sorry for inconvenience. Okay, it started, fortunately. So up to here we have already discussed, we were putting the values here. This is 10G and G is 9.8. So we have got the relation R1 plus R2 means sum of normal reactions upward. So R1 plus R2 plus R1 plus R2 is equal to 98 Newton. So after that, we can consider second equation also, where we have written this normal reactions and the distances. Distances we have already written there. So here weights and then distance. Then so we can put the values. After putting the value here, we need R1. So R1 is unknown and distance is here minus R1 times K1G. K1G is 25 centimeters, so minus 0.25 R1, and then here distance of weight W1 is just 5 centimeter, so it is 0.05 W1, and distance of R2 from here is 25 centimeter, so 0.25 R2 equal to 0. So if we simplify second equation, we get R2 minus R1, sorry, it is R1 minus R2. So R1 minus R2, we get as 11.76. Now what is left? We have to solve these equations. So just add 1 and 2. You will get R1, and then you can put the value of R1 to get R2. So R1 will be equal to 54.88 Newton, and R2 will be equal to 43.12 Newton. So I think you have understood, but let's revise it once again so that thing may become clear, because there was slight disturbance. So the situation is like this. This is point. Here its weight is acting, and weight of the rod is given as 4 kg. 4 kg is acting here at 5 centimeter distance. This is distance. This P, not P. This is G, and this is P, where there is another weight of 6 kg is acting. This separation is 5 centimeter, and here leaving 10 centimeter, there is one knife is K1, and its normal reaction will be R1 here. There is another knife is here, that this distance is also 10 centimeter. So this is K2, and normal reaction will be R2, right? So here we consider the torque in the two cases, and we take this positive and this direction as negative. So what do we observe? This is positive, this will be positive, this will be negative, but system should be in a rotational equilibrium. So when they are in equilibrium, then we can write that the normal reactions R1, R2 must be balanced by weights. So 6 and 4, 10 times 9.8. So 10 into 9.8. So this will be first equation. And then we consider rotational equilibrium. For that we take clockwise and anti-clockwise moment. So this is anti-clockwise. So we take this distance and force acting on it. So we can write R1. So here what is happening? Here weight is 6 kg, so this is like this. So we take moment for this, and then we take moment for this positive, and we take moment for this negative. The same thing we can write that minus R1. Then if we are taking R1, then distance of K1 from G, so K1G, and then these two are positive. For first weight it is positive, for second weight, for this R2 it is positive. So then we write R2 times distance of R2 from here. So this is K2G, this point is K2, so K2G, and then third one, this weight. So for this we write W1 times PG equal to 0, and then we can put the values, and then we will arrive at the equations, and hence we can get R1 and R2. I think now thing is clear. Okay, there is another question that is also interesting question, and here we have to consider that this ladder is in rotational equilibrium, so all forces will get balanced. A 3-meter long ladder weighing 20 kg leans on a frictionless wall here. Its feet rest on the floor 1 meter from the wall. So this distance is 1 meter, and you know that weight of the ladder will lie at its midpoint, that is center of gravity. So here weight is shown W, and this distance is 2√2 meter. Easily you can calculate, because this is 3, this is 1, so Pythagoras theorem will hold. One force will act at this point, and another force here, normal reaction at this point, will act. This is W1, and resultant here there is another force F1 is shown. So here we have to take moments, and calculation is done for find the reaction forces of the wall and the floor. So reaction forces are to be found. So N, F1, F2. So this is F2, this is F1 are to be found. So let's proceed how to evaluate it. So evaluation is again simple. Ladder AB is 3 meter long, and it's put A is at distance AC 1 meter from the wall. So situation, either we can draw different forces here so that thing may become clear. So here this situation, this is 3 meter, here its weight is acting W, and this is 1 meter, this is 2√2 meter, this is 3 meter. Here one force is acting, and here there is Darwin reaction, there is another force. So this Darwin reaction, there is F1. So different forces are there. So there is one force here. If it is F2, this is F1. Now, so what we do? The ladder AB is 3 meter long. It's put A is at distance. A is at distance. This is A. This is C. So which is 1 meter, and from the wall, and from Pythagoras BC equal to, here this is ball, BC equal to 2√2 meter. The forces on the ladder are its weight. As I told you, weight is downward, acting at its center of gravity D. At this point, it's the center of gravity. Center of gravity lies at the midpoint. Now, the reaction forces F1 and F2 of the wall and the floor. So here this is reaction force of wall, this is F1, this is F2. Reaction forces F1 F2 of the wall and floor respectively. Force F1 is perpendicular to the wall, that is shown there, and F2 is resolved into two components, the normal reaction N and the force of friction. So here there must be friction, otherwise this ladder will slip. So this F is resolved into friction. So there will be two components. One will be friction, which will oppose the motion. Another will be perpendicular, which will balance the weight. So we can say for translational equilibrium, it should not move, right? So normal reaction and weight must be equal. So this is the first condition. Now taking the forces in the horizontal direction. So here taking the force in the horizontal direction. So horizontal direction force means there will be friction. Frictional force is F, and F1 force is acting in this direction. So they will also be equal. And when we consider rotational equilibrium, it means force into perpendicular we will take. So if you take this force, then its perpendicular is BC. So that is why we write 2 root F1 minus. Here, what about this? For this weight, if weight is acting, so what is perpendicular distance? So this perpendicular distance should be taken, which will be half of AC. Total AC is 1 meter. So here 1 by 2 meters should be taken. So that is why this is equation. Now we can put the values. So W equal to given hai. Here W is given, and then N we can get, and then we can get F1 W upon this, and then F equal to. So after solving these two things we will get, and then in order to find F2 we can take the resultant of frictional force. So this is F2, right? So this is frictional force and this is normal reaction. They are mutually perpendicular. So here we can find F2 by using Pythagoras theorem, and then if we want to find out what is the angle, so angle can be found by using tan theta, and that will be around 80 degree. So I think you have understood. Once again, if you wish, I can explain you the situation, what is happening. So situation is simple. This is ladder, it is midpoint, its weight will act in downward direction. Here there will be one force in this direction, and this force, say this is F2, and there is normal reaction, so that will be F1. Now this distance is 3 meter, so this is 1 meter, this will be 2 root 2, correct? And then this is normal reaction, and there will be frictional force in this direction, so that this ladder may not slip in this direction. So here we can say that F2 is a resultant of normal reaction plus frictional force. This is one case, and body should not move. First thing, if we consider translational motion, means it should not slide in this direction. So one frictional force is acting in this direction, this force is acting in this direction. They must be equal. Similarly, for rotational equilibrium, we have to consider the forces. Here force into perpendicular, F1 into perpendicular, and here this is also another force. So its perpendicular distance should be considered. So they must be equal and opposite. So two conditions we have to check here. One is a rotational equilibrium, another is translational equilibrium, and after that we will get the values. Then comes the next concept, that is called moment of inertia. So moment of inertia, MI is equal to mass times distance square. It is generally denoted as I, and if we write the similarity between translational motion and rotational motion, so inertia will play the same role as mass plays, right? Like when we write kinetic energy here, what do we write? We write 1 by 2 mv square. So in case of rotational motion, if we write kinetic energy, in that case we will write, in place of m we will write I, moment of inertia, let's write it as I, and then angular velocity will be taken into consideration. So I omega square. Similarly, any other thing, like if we write here F equal to ma, so here force will be replaced by torque, and m will be replaced by I and A acceleration, this is linear acceleration. So here we will consider angular acceleration. So similarly, wherever mass comes in translational motion, so in case of rotational motion, we will make use of moment of inertia. So moment of inertia is a very good concept, and for this, suppose this is axis of rotation and there is mass, say at distance r1, say this is m1, there is another mass, say m2 at r2 distance, there is third mass here m3 at r3 distance. In that case, suppose we want to find out moment of inertia, so mi will be sum of all. So either you write here separately the values. So what do you get? You will get m1 r1 square plus m2 r2 square plus m3 r3 square and so on. So here there is one important term that is called radius of gyration. So when we consider radius of gyration, in that case, say radius of gyration is k. In that case, what do? We write moment of inertia mi as mk square, where m is total mass and k is radius of gyration, which can be found by r1 square plus r2 square plus r3 square and so on plus rn square whole divided by n. So this is how we can find. First of all, we take square, we do squares of distances from axis of rotation, and we find their sum, and then we divide by n, then do square root. Now here you are given this axis of rotation, this center point, so this will be L by 2, this is L by 2, and we can find moment of inertia here. A light rod of length L with a pair of masses rotating about an axis through the center of mass of the system and perpendicular to rod. The total mass of the system is M. So moment of inertia can be found for this and for this separately. The same thing is given here. M by 2 mass, perpendicular distance is square, plus M by 2 mass, perpendicular distance is square. So this is how we can find moment of inertia of the rod. You have understood, I think. The situation is like this. Once again, I can tell you, this is axis of rotation, and this is the axis of rotation, and here there are two masses. One mass is here, say m1 at distance r1. Another mass is here at distance r2. So in this case, moment of inertia you will write like m1 r1 square plus m2 r2 square. But in our question, m1 equal to m2 equal to capital M by 2 is given, and this is midpoint, this is L by 2, this is L by 2. So we can replace m1 m2 by m, and here r1 as L by 2 and r2 as L by 2. So we can get moment of inertia that is shown here. So I think it is clear. Now I told you about radius of gyration. The same thing here mentioned, and as a measure of the way in which the mass of a rotating body is distributed with respect to the axis of rotation, we can define a new parameter called the radius of gyration. And here radius of gyration of certain points is given, like k for a rod about the perpendicular axis and its midpoint, radius of gyration is given by k square equal to L square by 12, or k equal to L root 12. Similarly, k equal to r by 2 for the circular disc about the diameter. The length k is geometric property of the body. The radius of gyration of a body about an axis may be defined. So this definition you have to memorize, because this is important, but generally definition is not asked, but you should know it. Its evaluation numerically is frequently asked, so you should know. It is called the radius of gyration of a body about an axis may be defined as the distance from the axis of mass point whose mass is equal to the mass of the whole body and the whose moments of inertia is equal to the moment of inertia of the body about the axis. Thus, the moment of inertia of a rigid body depends on the mass of the body, its shape and size, distribution of mass about the axis of the rotation, and the position and orientation of the axis of rotation. So, if you consider the unit of moment of inertia, so as you know, moment of inertia is really mr square, right? So here this will be kg and this is meter square. So unit will be like this. So let's see what is next. Here some examples are given where in a daily life the concept of moment of inertia is used, like flywheel whose entire mass or large mass is concentrated on its rim so that it can continue to move. So we can read it. The property of this extremely important quantity I as a measure of rotational inertia of the body has been put to a great practical uses you should know, like the machines such as steam engine and the automobile engine that produce rotational motion have a disc with a large moment of inertia called a flywheel. Because of its large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows a gradual change in the speed and prevents jerky motions, whereby ensuring a smooth ride for the passengers on the vehicle. So this is important concept. There will be some numericals based on this concept. So we will see, but here let's see some other thing. Here moment of inertia of different bodies are given, like body is thin circular ring of radius r and its axis of rotation perpendicular to plane at the center. It is shown here. This is axis of rotation. Body can rotate like this. So its moment of inertia is mr square. Second case, thin circular ring radius r and axis is diameter like this, so rotation, so mr square by 2. Then thin rod of length L, perpendicular rod at a midpoint, so rotation is like this, so ml square by 12. If you consider circular disc of radius r, so here axis will be perpendicular disc and center, it is shown here. Its moment of inertia will be mr square by 2. These things you have to memorize, they are important. Circular disc radius r, about the diameter is the rotational axis. So here, so body will rotate like this and its moment of inertia will be mr square by 4. Similarly, if you consider hollow cylinder, its moment of inertia will be mr square, whereas solid cylinder has moment of inertia mr square by 2 and the solid sphere has moment of inertia 2 by 5 mr square. So these are some basic concepts that you have to memorize. So we will continue with the kinematics of rotational motion and other related concepts in next lecture. Thank you for watching. Team Educate.